Hey, uh, yeah, thank you so much for sticking to uh, the last lecture of today. Okay, so the last topic of today is about maximizing a submodular function, and um, so you know the discrete case, the set function case dates back to 1970s. And it's an old problem, although there are so many, I guess, applications in many areas. So like lots of uh, problems involving discrete quantities, even in machine learning, they model the problems as a modular set function maximization and run a simple greedy algorithm. Okay? And what recently for the last 10 years, people have noticed that the continuous version of the problem is also very useful in many, many problem domains. And when you take a continuous problem, you can find some, I guess, nice and efficient first order algorithm like gradient descent. And, and that's what I'm going to explain at the end of today's lecture. Okay? So I'm gonna start with uh, the problem of maximizing a submodular set function, and I will explain uh, the problem subject to some possibly complex constraint, and I will also talk about the continuous version of the problem. Okay. Okay, so again, we have a set function and it's submodular if it satisfies this inequality. So you take two subsets A and B. We say that the function is submodular if the summation of the function values is at least the union value and the intersection value, and it's equivalent to satisfying this diminishing marginal returns property. Okay. Again, like I didn't give you this analogy. If you go to a buffet restaurant, I guess the first plate gives you the most happiness. When you start the second plate, it gives you a less happiness. And, at some point, like having more food actually makes you less happy. And it's an analogy. We talked about the coverage function, and this is one example. Like you have some map, and you are building some like surveillance cameras, and you measure the areas covered by the surveillance cameras, and that gives you a modular function. And another interesting example is coming from the utility maximization problem. So what I do is the following. So let's say I have some pool of employees, and individual employees have stochastic performance values. Okay. And what I want to do is I take a collection of employees. Maybe I have a budget or I have a limited number of positions for people. And I hire a team of employees so as to maximize a certain group utility. It's not the simple summation of their values, but it's more about some nonlinear quantity. So if you look at the first one, you take the expected value of the maximum performance. Let's say you can imagine a sports game team. So you hire a pool of players and athletes, and your ultimate goal is to take the gold medal. And when you imagine a gold medal, I guess the highest performance is what matters. So this is what's important. You can also take the, I guess, square root of summation of this utility, and you take the expected value. Even for the stochastic setting, these functions give you a submodular function. Okay. Okay, so I'm interested in the problem of maximizing a submodular function. That is, uh, okay, I have a submodular function and I want to take a subset that maximizes the function value. But I care about the monotone case. What it means is if you take a larger set, it gives you a higher function value. If you take two subsets A and B, where A is included in B, the value of B is greater than or equal to the value of A. Okay. For the monotone case, if you don't have any restrictions on which subset you take, then the optimal value or the subset that's maximizing the function value will be the entire element set. Okay. So for the monotone, for a monotone submodular function, it makes sense to impose some constraints. So let's say I have a number of positions. I have a limit on the number of available positions. I can hire, let's say, 10 people out of like 10,000 candidates. Okay, then that can be captured by this cardinality constraint set. You can also model some kind of knapsack constraint. So maybe hiring individual employees have certain prices to be hired, and I have a budget B on the amount of budget I can spend. Okay. We can also consider like the matroid constraint. So like the one example is there's a partition of the elements, and I can hire at most one person from each partition. Okay, that can be modeled using matroid. So I'm allowed to take an independent set of a matroid. That's another example. It appears in many numerous applications like online freelancing platforms or team selection. You want to hire a pool of people, but when their intersection is nonlinear, the group utility can be a linear function over the players that chosen to be in the team. And also, if you imagine the online shopping mall, it recommends a certain combination of items. It's called the assortment problem. And what is the best assortment of items that potentially leads to maximum rate of clicks? That's on another example. And also influence maximization. So we have a network of people in a social media platform. Then you want to select a few influencers so that they can, if you invest something on these few influencers, the information spreads in the fastest possible speed, something like this. And also even for machine learning, you want to select a subset of variables, and you have a limit on the number of variables you can choose, but you still want to kind of achieve the highest accuracy given this budget. Document summarization or image summarization. So you have a video, and you want to, let's say, take a screenshot of 10 scenes of that long video that best summarizes the entire video. That's another example, and also in other problems as well. So submodular function maximization, even though the minimization problem can be solved in polynomial time using, we talked about the polynomial time algorithms, but the maximization problem is NP hard. NP hard, it means that you don't expect to have a polynomial time algorithm unless the complexity class P collapses to, or NP collapses to the class P. But there's a nice polynomial time constant approximation algorithm. And what is an approximation algorithm? So we say that a solution S bar is alpha approximate if its value is at least some alpha fraction of the optimal value. Okay? And you say that your algorithm is an alpha approximation algorithm if its value, it guarantees at least an alpha approximate solution for every scenario of the problem, every instance of the problem. Okay? So, and if we say that there's a constant approximation algorithm if there exists some global constant that doesn't depend on your problem instances. It's if you give me any, if you imagine the, matching problem, we saw that, a greedy algorithm always gives you a maximal matching. And if you have a maximal matching, its number of edges is at least half of the maximum size of a matching. So that greedy algorithm is a 0.5 approximation algorithm for bipartite matching. Okay, that's what it is. But for submodular maximization, we can achieve 1 minus 1 over E, which is approximately 0.63 for submodular function maximization. And the algorithm is pretty simple like this. So what you do is you start with the empty set. Okay? And until you reach the limit on the number of elements you choose, you pick an element that maximizes the marginal return. Okay. So among the elements that have not been included, you choose the one that has maximum possible marginal return. Okay. And it's proven that it's proved that it gives you a 1 minus 1 over E approximation. And let's prove this together. It's not too difficult. Okay. The proof is the following. So let S star be an optimal subset which achieves its maximum possible value, and let E1, E2, EK be the sequence of elements chosen by the algorithm. So E1 achieves the maximum marginal return, and then E2, given your set is, the singleton E1, E2 is the one maximizing the marginal return. And you have the subset of two elements, E1 and E2. E3 is the one maximizing the marginal return, and so forth. Okay? This is a sequence of items you choose. And so what I do is the following. So let Si is, you take the first I element for I from 1 to K. Then my final set, S bar, is nothing but Sk. Okay, and we claim the following. For each I, f of S star, which is the maximum possible value, it should be greater than or equal to f of Si. But there's an upper bound on this S star value, which is here. 1 minus 1 over K to the I f of S star. You can argue this. Okay. We're going to prove this for each I from 1 to K. 0 to K. 0, 1 to K. For the case when I equals 0, we assume that fs0 is the f of empty set, which has value 0. And the left-hand side becomes f of s star, and the right-hand side becomes f of s star because I equals 0. So the trivially holds. We're gonna prove. and assume that f of s star minus f of s I minus 1 is at most 1 minus 1 over k to the I minus 1 f of s star for some I greater than or equal to 1. And I argue by induction, and let's look at S of I. Okay. All right. Right. So let's look at f of s star minus f of s I minus 1. Okay. Now, let me look at the elements that are outside this subset S I minus 1. Okay. Let me denote them by, let's say, how do I, let's say P1 through PL. Okay. So L is at most K because S star is an optimal solution with at most K elements. So L is bounded above by K. So my claim is that this is less than or equal to for all elements in S star minus Si minus 1, f of Si minus 1 union E minus f of Si minus 1. This is what I want to claim using the diminishing marginal returns property. Uh, okay. Right. So let's prove this. So this is at most f of s star union Si minus 1 minus f of Si minus 1. And this is because my function is assumed to be monotone. You take a subset larger than S star, and we kept Si minus 1 the same. So we have this inequality. This is by the monotonicity property. Okay. And this is equal to f of Si minus 1 union this L elements minus f of Si minus 1. Okay. So far, so good. So this is equal to the following. This is equal to f of Si minus 1 union P1 PL minus f. I'm going to define a telescoping sum. Si minus 1 union P1 up to PL minus 1. And here I have Si minus 1 union P1 through PL minus 1 and minus f of Si minus 1 union P1 through PL minus 2. And so forth, and you have Si minus 1 union P1 minus f of Si minus 1. Yeah. Oh, well, I mean, this thing is the by the monotonicity of the function. Okay. Now I have rewritten this the right hand side. Equality holds. Okay. This is not equal. This is plus. Okay. The reason that we get this equality. Sorry. because this thing cancels by the telescoping sum. Okay. But now is the point where you apply the diminishing marginal returns property. So this thing, what we take is we are adding PL to here. We have the SI minus 1. We take the first L minus 1 element, and here we have the elements of the PL. So the first one, the first term is less than or equal to f of s minus 1 union PL minus f of si minus 1. But now this is the point where you use the diminishing marginal returns property. Now you look at this thing. We are including PL minus 1 to this set. Okay, this set includes up to the first L minus 2 elements, and I have PL minus 1 here. So the difference is less than or equal to f of s I minus 1 union PL minus 1 minus f of s I minus 1. Then you repeat this thing. Oh. Plus, you repeat this thing up to f of s minus 1 union p1 minus f of si minus 1. So this is equal to summation of E belongs to S star minus S minus 1. F of Si minus 1 union E minus F of Si minus 1. Okay. Now we got this argument. Whew. And let's see. Now, what I claim is the following. So E doesn't belong to S minus 1. Okay. Now you can add E to Si minus 1. Now, what is EI? Well, EI is the element chosen after Si minus 1. And we chose EI so that it maximizes the marginal return. So what it means is this thing is less than or equal to E S star Si minus 1 f of Si minus f of Si minus 1. Because instead of this element E, you can choose EI, which is the element that maximizes the marginal return. And here Si is Si minus 1 union EI. Okay, now this thing is equal to S star I minus 1 f of Si minus f of Si minus 1. This is at most K times f of Si minus f of I minus 1. Okay. Because S star can take at most K elements. So what we proved is the following. We proved that f of S star minus f of Si minus 1 is at most K times f of Si minus f of Si minus 1. Now I'm going to move K times f of Si to the left-hand side and fs of I minus 1 to the right-hand side. And this thing is equivalent to f of S star minus f of Si. It's at most 1 minus 1 over k times f of s star minus f of si minus 1. I just, you can just do a simple algebra, then you get this one. And now we are done with the claim. By the induction hypothesis, this is less than or equal to 1 minus 1 over k to the I minus 1. This is equal to 1 minus 1 over k to the I times f of s star minus f of s star. Okay. Just to summarize, by the claim, for I from 0 to k, we know that f of s star minus f of si is at most 1 minus 1 over k to the I f of s star. Now, if you choose I equals k, then f of s star minus f of sk, where sk is the solution returned by my algorithm, which is s bar. So most 1 minus 1 over k to the k f of s star. And, this looks like the 1 over e, where e is a natural constant. So this is at most 1 over e, where e is like something like 2.7. And this proves that 1 minus 1 over e times f of s star is at most f of s bar. Okay. So let's get back. So the algorithm is that until we hit the limit on the number of elements, we choose an element that is not part of my current set. Among those elements, I take the one maximizing the marginal return. Now, if you do this, it gives you a 1 minus 1 over e approximation algorithm. Okay. Any question? Yeah. Yeah. Okay. Yeah. I was really messy. Let me delete all this. And great. So this thing is equal to f of s star union p1 through pl minus f of not s star, si minus 1 union f of si minus. So far so good. Okay, so now I expand this summation, and this is si minus 1 union p1 minus f of si minus 1 plus f of si minus 1 union p1 p2 minus f of si minus 1 union p1. Okay, if you do this, you can cancel, no, you can cancel this term and this term. And so you repeat this thing until you get plus f of si minus 1 union the first L element minus f of si minus 1 union p1 through pl minus 1. Okay? All right. So then this thing is fine. We get the same thing. And what about the second difference? Si minus 1 is a subset of Si minus 1 union P1. Okay. Now, if you look at this difference, this is the marginal return of adding element P2 to this subset. Then the marginal return increases if you take a smaller subset. And I take Si minus 1 as a subset of this thing. So this thing is at most f of Si minus 1. And now I'm adding P2 to this subset Si minus 1. Does this make sense? Again, you are adding P2 to this subset. Now you're adding P2 to Si minus 1. You're adding P2, you're adding the same element to a superset, Si minus 1 union P1. But you're adding this element to a subset Si minus 1. This is a definition of the diminishing marginal returns property. Does this make sense? Okay. And you look at this thing, PL is the only difference. So I'm measuring the marginal return of adding the element PL to this subset, Si minus 1, P1 up to PL minus 1. So instead of adding the element PL to that subset, I take Si minus 1, which is a subset. So this is at most f of Si minus 1 union PL minus f of Si minus 1. Okay, and that gives you the summation. Okay. Any other question? All right, great. So, okay, so for the case of monotone submodular function maximization, we saw this 1 minus 1 over E approximation. But even for a knapsack constraint setting, you can extend this greedy algorithm to capture kind of heterogeneous weights. And that gives you 1 minus 1 over E approximation. And for a matroid constraint and for a system of linear constraints, you can achieve the same approximation ratio. Okay. But these two, their algorithms are quite different from this simple greedy algorithm. That's what we're going to briefly touch upon. So the idea is the following. So we have a matroid constraint. So there are three parts. So what we do is we take continuous relaxation of this discrete problem. Okay. So our solution space is a set of independent sets of a matroid. Okay. So this is a discrete problem, but we take a continuous relaxation of it, and we solve the continuous relaxation somehow. And then, because this is a continuous relaxation, the resulting solution does not necessarily correspond to a subset. Then in that case, we round the solution to get a subset. That is the basic outline. And we take something called a multilinear extension to relax the objective function. And we take the polymatroid to replace the solution set. And then we apply something called a continuous greedy algorithm. It's an extension of the greedy algorithm we talked about. And we apply the method called pi pitch rounding to get a subset from this fractional solution. Okay. Any question? So I'm going to explain one by one. So what is the multilinear extension? Well, we have a set function f, and given a set function f, my multilinear extension is given in this term. So for each subset S, I have the function value. Now you have the product of these multiple variables. So for the element in set S, you take the variable xv. For the elements that are not contained in the subset, you take 1 minus xv. Okay. So when you take a 0, 1 vector, okay, which corresponds to a subset S, then in this summation, only f of S survives because this product will have value 1 if and only if this xv has value 1 and xv here for the element that are not included in the subset 0. Okay. So this extension agrees on all subsets, but it can be defined over the points in the 0, 1 box that can take fractional values. Okay. So this is extend continuous value, and it can be written as the expectation of some random function where the subset S is randomly chosen, where each element is sampled with probability of xv. Okay, so that's basically what it is. All right. So and the set of independence, the collection of independent sets for a matroid can be relaxed with this matroid, where I have this rank function. So this is the almost like the extended polymatroid we talked about from the previous lecture, but I have this 0, 1 bounds. So I mentioned that the rank function of a matroid gives you a submodular function. So I took that one, and you define this polymatroid by applying this 0, 1 bound. So this is almost like the extended polymatroid from the previous lecture. Okay. Now I had a collection of independent sets which are discrete. Now I define this polytope, which is continuous. Okay. So you had this submodular function maximization problem, which is a discrete optimization problem. But now I have the continuous function in the objective, and I have a polytope as a constraint set. Now this is a continuous problem. Okay. And in particular, this is a relaxation. So if you solve this continuous problem, its value is at least the value of the discrete problem. Okay. Any question? I can see that I'm kind of losing you. Uh, I guess it can be quite technical, but the idea again is that I have this discrete problem of maximizing a submodular function. So the question is, which subset maximizes this function value? Okay. When you have this complex matroid in independent set constraints, it's not as simple as a greedy setting where you can always choose whichever element that maximizes the marginal return. But for a matroid, you need to keep that matroid structure, so you cannot add an arbitrary element to it, even though it maximizes the marginal return. To capture that, we are kind of taking some continuous approximation of the problem. That's what it is. Okay, so there's this algorithm called continuous greedy algorithm. Okay, this is a continuous trajectory. So this algorithm is not like discrete. Let's look at this. So you have this trajectory of the solution x of t. So t is the time index. It goes from 0 to 1. My initial solution is x sub 0. And I stop when t equals 1. Okay, so then x of t is given by this differential equation. So the rate of change at time t is given by this function v of x. So here, I have a polytope. And let's say I have my solution x of t. Okay. And I compute the gradient of the multilinear extension. Let's say the gradient goes towards this way. Okay. So it's gradient f of x of t. Okay. Let me take the value here. Again, I have my current solution at time t given here. And to maximize my question is, how do you maximize this continuous function over this polytope? So to do so, I take the gradient at this point. Then you, like we do for Frank proof, for those of you who have taken my convex optimization course, you find the vertex V that maximizes this linear function defined by this gradient direction. So you take this solution V, okay? And let's say this is the direction V. And using that, you are changing your solution based on this. So dx dt over dx. This is V xt. So the rate of change at t is given by v of x of t. Okay. Let me stop here. So if you run this algorithm, then what you can prove is that the final solution at time t equals 1. If you measure the value of the continuous multilinear extension, its value is at least 1 minus 1 over e times the optimal value of the set function. This is the what they proved. Okay. Now, okay, so we got this solution x of 1, which is fractional. Now you can apply a randomized rounding algorithm to generate a set S whose expected value is at least as large as the value of the multilinear extension. So if you combine this, the continuous greedy algorithm and the rounding approach, what the final outcome is that you get a random subset S whose expected value is at least the value of the multilinear extension, which is at least 1 minus 1 over e fraction of the optimal subset's value. So combining all these things, you get a 1 minus 1 over e approximation algorithm for the problem. Okay. Any question? Yeah. No, V is a direction that corresponds to X. So X is my solution here. And I compute the direction of movement by like the Frank-Hoof type argument. And just V of X, it's just the direction V is a function of X. That's the notation. But V is a vector. Yeah.
Are we assuming that our original objective function x should be always differentiable because we are taking the gradient?
Well, so multilinear extension by definition is differentiable. So this is a product. This is a multilinear production. This is kind of multilinear functions. You take multinomials. By definition, is differentiable. You can compute the gradient in easily. Not easily. Like you can. Yeah. I mean, you have to go through all the subsets, but you can differentiate this multinomial. There's a closed form expression for that. Any other question? 네. Well, I got interested in this problem because, I guess people have a common belief that combinatorial problems are harder to solve. So but we have this bunch of nice algorithms like gradient descent or Frankel stochastic gradient descent that work really nice for continuous problems. So then the question is, can you bridge between this discrete problem and continuous problem somehow? And I think in 2017, there was a workshop in the Simons Institute with the title of Bridging Continuous and Discrete Optimization Problems. And I think submodular maximization is one example. So we have this discrete problem, but we are defining a continuous relaxation and apply the continuous the method that guarantees the best possible approximation ratio. This is I guess, the example that represents, the nice bridge between continuous and discrete problems. Okay. So let's summarize. Well, what we've done is, again, we took the continuous relaxation of the objective and continuous relaxation of the constraint set, and we solved the continuous problem using the continuous optimization method. And later on, we apply the rounding procedure. Okay. That was the approach. And well, in fact, what people have observed is that, so we talked about this multilinear extension, which is directly coming from submodular set functions. But people have noticed that there are similar classes of continuous functions, not just multilinear extension, which resemble which keep some properties, some important properties of the multilinear extension. And in fact, those functions arise in many applications in machine learning. That's why people have started studying this class of functions, which are called continuous submodular functions, for the last 10 years. So I'm going to explain what they are. So look at this multilinear extension. Okay, so multilinear extension. And it is known to satisfy this property called diminishing returns property. So now I'm talking about continuous functions. Okay, so the argument are some arbitrary vectors. Okay, let's say I take some coordinate. Okay, and I increase this value by delta. And I measure the gap between the change and the original point. Okay, if y is a vector that's larger than x in component y's, then the marginal return is always greater for smaller vectors than the larger one. So this is continuous analog of the diminishing marginal returns property for submodular set functions. Okay, it is not convex nor concave, but what you can argue is that if you take a non-negative direction, along the non-negative direction, the function is concave. Okay, this is not the function itself is not convex nor concave, but if you move along the non-negative uniform direction, it's concave, and it's called the up-concave. Okay. Moreover, if you look at this multilinear extension, you can argue that the function is smooth. This is not convex nor concave, but the function is smooth. Okay. we define smoothness in terms of this difference in the gradient. We say that your function is smooth if the gap between two gradients is boundable by the gap between the 2 points. Then we say that the function is smooth. So we have these properties, the diminishing returns property, and some kind of a concavity property, and also the smoothness. For any classes of function that satisfy these three properties, we can design an algorithm. That's what I'm going to explain. So that's the function that we see. So continuous function is DR-submodular, where DR stands for diminishing returns property. If we have this property, and in fact, the up concavity, meaning that if you move along the all non-negative direction, the function is concave. If you assume this this diminishing returns property, then up concavity just directly follows. That's what you can prove. Okay. And in terms of like gradient and the Hessian, we know that a function is convex if and only if the second derivative is non-negative, or the Hessian is positive semi-definite. But for submodular functions, the DR-submodular functions, if your function is twice differentiable, then its Hessian is all non-positive matrix. Like all entries are non-positive, then you can prove that the function is DR-submodular. Okay, and it applies in many examples like utility function and this log determinant, and this is kind of like the some functions and quadratic functions with matrix whose entries are all non-positive are examples. And in fact, they appear in many problems like isotonic regression and robust budget allocation, and also resource allocation. And for Edwards problem, many problems can use these continuous versions of DR-submodular functions. All right. So now the question is, we take this submodular function maximization problem. So my function is continuous DR-submodular, and it's monotone. So meaning if you take two vectors where one vector is larger than the other one component-wise, and you have a convex constraint set, but it has some properties like this, then you can design some algorithm called the conditional gradient method, which is also called the Frank-Wolf algorithm. Well, I guess this is the Frank-Wolf algorithm for submodular case is a little bit different in terms of the update. If you remember what we've learned for the convex case, we took this original point and the vertex, we took a convex combination between two for the convex case, but the update rule is a little bit different. So the algorithm is here. You can view this conditional gradient algorithm as a discretization of the continuous greedy algorithm. So here, at every step, we compute the direction. We solve this linear optimization over this convex set C. Okay, like we did for the polytope case. So we have this polytope, and I have my current solution xt minus 1, and I compute the gradient. Let's say the gradient is f of xt minus 1. So if you move along this gradient direction, you are increasing your function value. So instead of moving along this direction, what the Frank-Wolf algorithm does is to optimize the corresponding linear function. And you get this solution, which is Vt. And you take this vector Vt, you add 1 over capital T multiple of this direction Vt to your current solution. That's your next solution. And you repeat this procedure for capital T iterations. And this is a first order method because your algorithm runs with the gradient information. Any question? Yeah. Well, gradient descent, you move along this direction. Well, you take this direction VT. So, I mean, it also depends on where the 0 point is located. Let's say the vector has direction this way. You're going to move along this direction. So this is clearly different from gradient descent. But what Frank-Wolf does, for convex case, you typically have something like xt minus 1 plus 1 over t times vt minus xt minus 1 for the convex case, in which case you are taking a convex combination between xt minus 1 and vt for the convex case. But when you have a submodular function, you don't have xt minus 1 right here. This is a difference, but except for this last part, this algorithm is the same as the Frank-Wolf algorithm for the convex case. Okay. Any other question? Yeah. Right. That's a good question. So if you imagine the polymatroid, so when C is given by a polymatroid or extended polymatroid, the linear optimization over a polymatroid can be done by a greedy algorithm. We talked about that, right? Depending on the situation, yeah. So a Frank-Wolf algorithm is used. So you are optimizing a linear function, whereas if you think about like projected gradient descent, you are minimizing the quadratic objective. So sometimes when you are given a polyhedron like this, optimizing a linear function is a lot easier than optimizing a quadratic function. That's the motivation for Frank-Wolf. Okay. Just to give you one more motivation, like for the Frank-Wolf is used for like low rank matrix completion problems where the linear optimization corresponds to finding on the largest singular value, which can be solved by the power method. But if you optimize a quadratic function, you have to compute the full singular value decomposition, which is a lot more expensive. So Frank-Wolf algorithm is used in many places. Okay. Any other questions? All right. Okay. So then you can prove this result. Okay. So this is nice. I mean, at least this is nice to me. So you compute the final solution and you measure its value. It's at least 1 minus 1 over e fraction of the optimal value, but there's an additive error of this term. Okay. So for this kind of problem, we say that the convergence rate is 1 over t. Okay. Which means that if you increase the value t, this error, the additive error, will reduce to 0. And the rate of the convergence is 1 over t. Okay. And then I guess if any of you who have taken my convex optimization course at KAIST, 1 over t rate is quite fast, which can be achieved for smooth functions. If you run gradient descent, we have 1 over root t. So 1 over t is quite fast. Okay. So even for this non-convex problem, although we have this approximation error, the rate of convergence to whatever we can achieve is fast. And this is due to smoothness. Okay. I found it quite fascinating. Yeah. Again, beta smoothness is you take the gradient, you take two functions, two vectors, x and y, and you measure their gradient difference. Okay, and you measure the gap. If x and y are close, then their gradients not really change. Okay, so here this is bounded above by beta times x minus y L2. One example of a non-smooth function is the absolute value function. Okay, this is non-smooth around the origin because as soon as x become positive, the gradient is +1, and when x becomes negative, the gradient becomes -1. So by a very small perturbation, the gap becomes 2, although the right-hand side becomes 0. So this is non-smooth, but the multilinear extension is known to be smooth. And if you take any smooth functions, I guess you can guarantee this. Any other question? Yeah, I was going to actually prove this theorem with you, but well, in fact, the proof is not too difficult. So well, I have included the proof in the lecture notes. So the point you use is you apply smoothness. Okay. So if your function is smooth, you can always approximate your function by a quadratic function. That's one part. And then you use the monotonicity. Okay. That's the only two components that are used in this proof. All right. So this is the end of today. Thank you so much for sticking to the lecture until now. And tomorrow, again, I will talk about something more possibly practically relevant. So the first topic will be about black box optimization. So I was working with some industry partners, and their problems were that I make some solution. Then after I make the solution, I can measure the objective value. Okay, it's not like the edge weights are given so that we can from which we can predict the optimal value, objective value, but you actually need to make decision first, and then you're allowed to observe the outcome. This is a black box optimization, and how do you solve, or how do you guarantee at least an approximate solution for this class? And the second topic will be about my recent research results which is about some reinforcement learning theory. All right. So thank you so much. I'll see you tomorrow.